Okay, so I want to look at then that second example for polar functions. And so, it just says here it is, it's the same, well, actually the same structure. It's a polar cardioid. It says find where there's a horizontal and a vertical tangent line. And so, again, thinking about like in parametrics, that happens when either the numerator or the denominator is equal to zero. So we don't necessarily have to find the entire, like we don't have to put it together to get the entire derivative, because we just focus on either the numerator or the denominator, depending on which part of the question we're answering. But remember, to find dy dx, you have to compare dy d theta over dx d theta. And if you're trying to show that there is a horizontal tangent line, the slope would be zero. And remember, so that's sort of equivalent to finding out, well, when is that equal to zero? That'll help us find a horizontal, because that, like that slope of zero, it will be determined by that particular function. And then if you wanted to find an undefined slope, we need the denominator zero. So that would give you where there'd be a vertical tangent line. And again, don't forget x is equal to r cosine of theta, and y is equal to r sine of theta. So I guess we can do the horizontal one first. So we want to find dy d theta. So again, we start with y equals r sine of theta, and we take this derivative, we substitute what r is equal to. So y is equal to the quantity 2 minus 2 cosine of theta times sine of theta. And then we distribute. So we get 2 sine theta minus 2 cosine theta sine theta. Now, I think I mentioned that this is like, again, a cardioid, but because it's negative cosine, it's going to have its major axes in that direction. And so I'm anticipating for a horizontal tangent line, just kind of knowing what this graph looks like. So, there should be a horizontal tangent line there and one right there as well. So I'm anticipating two. I need to be very, very suspicious about anything I get right, I guess yellow, right there at that cusp, because at that cusp, it's too sharp for any kind of derivative. So I'm thinking that might come into play maybe for a vertical tangent line, but who knows? Okay, so here's my equation, right? There it is. So let's go ahead and take the derivative. So dy, oops, I want green this time. I get whatever, dark green maybe. So it's not quite as, let's try that one more time. Pen, color, let's go green. So dy d theta. So the derivative of 2 sine would be 2 cosine of theta. And then minus, and then we got a product rule. So derivative of 2 cosine would be negative 2 sine. Leave that sine alone. Plus, leave 2 cosine alone. And then derivative of sine, which is cosine. Okay. So then, so if we distribute, so we get 2 cosine of theta, and this becomes plus, because that, right, plus 2 sine squared of theta, and this becomes minus 2 cosine squared of theta. And so we want to set this equal to 0 because we're trying to find a horizontal tangent line, and that's when the numerator is 0. So we set it equal to 0. And the thing is that this is really close to Pythagorean theorem, but it's not. It's a double angle of cosine, but then we end up getting an expression with cosine 2 theta and a normal cosine theta, which I don't want. So my best strategy here is to write everything in the same trig function. So let's write sine squared into what its component is for cosine squared and try to factor this. And so remember, sine squared plus cosine squared is equal to 1. So when we solve this, we would be able to say 1 minus cosine squared would be sine squared. So 0 is equal to, leave this 2 cosine alone, plus, and then 2, and then instead of sine squared, call it 1 minus cosine squared. And then we also have minus this 2 cosine squared of theta. And so let's see what we have. I do notice they're all divisible by 2. So let's get rid of that. So we get cosine of theta. And now that 2 is gone, I could just say plus 1 minus cosine squared of theta minus cosine squared of theta. Because remember, we divided out the 2. So, and we have some like terms here. So 0 is equal to negative 2 cosine squared theta. And then we could say plus cosine theta plus 1. And I like my lead coefficient to be positive, so I'm going to divide out the negative. So 0 is equal to 2, there it is, 2 cosine squared theta minus cosine theta, and then minus 1. So again, this is, thinking back from solving trig equations, this is a quadratic. It's just your variable is cosine. And if it helps you to see it a little better, certainly then call that, what if it was 0 is equal to 2x squared minus x minus 1? Maybe you'd see the factoring a little bit, more clearly, 2x and x. And then I'd put a negative 1 here, a plus 1 there. That would guarantee my negative 1. It lets the middle terms add up. And so I would say, okay, x is equal to negative 1/2, or x is equal to 1. But then again, what was x? Oh yeah, that was cosine. So let's think about, when is cosine of theta equal to negative 1/2? And when is cosine of theta equal to 1? And so, so cosine of theta equals negative 1/2. And then we're just on one trip around the unit circle. Cosine depends on x. So I want to be over here in quadrants 2 and 3. So I want to make sure that I do have a ratio. There we go. One more time. There it is. So I do want to have a ratio of negative 1 to 2, or negative 1 to 2. So it's a 30-degree reference angle. I'm sorry. No, not 30-degree reference angle. It's a 60-degree reference angle. So that's 120, or 2 pi over 3, and 4 pi over 3. So it looks like theta is equal to 2 pi over 3, or 4 pi over 3. And then over here, when is cosine equal to 1? Cosine is equal to 1. Again, on the unit circle, you could either choose 0 or 2 pi. So theta is equal to 0 or 2 pi. Now, actually, remember how I talked about that suspicious point? It actually happened right here. Because think about it. When theta is 0, 2 times cosine, so cosine of 0 is 1. So you get 2 minus 2 is 0. So you actually get this point right here, that cusp. Now, that is not a horizontal tangent line. It's an undefined point. So I have to be a little bit knowledgeable of these cardioids, that this is extraneous solution, okay, because there's a cusp there. So it's not a horizontal tangent line at 0. And then 2 pi over 3 and 4 pi over 3. So that's probably equivalent to this guy right there. So again, thinking about our cardioid, if I draw that just a little bit bigger, so we could really kind of see this. So here's our cardioid coming around. And remember, the way that it's graphed, is like you kind of you're going out different radiuses. So as soon as I get to 120, let's say it's right there, like that point right there, at that instant, it kind of does look like it's the peak of my cardioid. So the horizontal tangent line looks like a slope of 0. And again, look at your angle. Your angle is going from the standard position out to here. That's like 120 degrees. So that worked out great. That as we kind of, again, we angled out till we got to 120 degrees. There we go. And then bam, there's our there's our horizontal tangent line. So it does ask us to find r comma theta. We just found theta to be 2 pi over 3. So let's go ahead and sub that in. So we need 2 minus 2 cosine of 2 pi over 3 to get the r value. So r is equal to 2 minus 2 cosine of 2 pi over 3. And so again, cosine of 2 pi over 3 is negative 1/2. So 2 minus 2 times negative 1/2 becomes 2 plus 1, or is equal to 3. And if I put in 4 pi over 3 to get the second one down here, if it kept going, right, let's keep going till we get to, to your 240 degrees. There it again is my horizontal tangent. I get the same radius, 3 out. So both points for the horizontal tangent line, so for the horizontal tangent line, r comma theta would be 3 comma 2 pi, oops, there it is, 2 pi over 3, and then 3 comma 4 pi over 3. And we said 0 was an extraneous solution because there's a cusp. Okay, so that's horizontal tangent lines. Now, vertical tangent lines, it appears there would be 3. And so again, looking at my graph, it sort of looks like, I guess if I pick maybe this red color, there seems to be one here, there seems to be one here, and there seems to be one here. But again, I should be wary, the cusp might come back out again. So let's find a vertical tangent line. And remember, vertical tangent lines, when you have your derivative, your slope formula, right? dy dx is equal to dy d theta over dx d theta. We're interested in dx d theta being 0 because that would be an undefined slope in this formula. So let's calculate dx d theta. In order to do that, we need what x is in terms of theta. So I'm writing quite big on this smartboard. Hopefully you have enough space on your paper, and if not, then maybe a little bit of additional paper is fine. So x equals r cosine theta. Remember, our function was 2 minus 2 cosine theta. So x is equal to quantity 2 minus 2 cosine of theta, and then cosine theta. Now, in hindsight, I probably should have started with this one because I'm not going to need to. Well, actually, I take that back. Maybe I will. I misspoke. Let's go ahead and distribute. So it's 2 cosine theta, and then minus 2 cosine squared theta. I was thinking this would just be in cosine, but the derivative, but it won't. Okay, so let's take the derivative, speaking of which. So dx d theta. So the derivative of 2 cos would be negative 2 sine. And then this 2 comes down, so minus 4 cosine to the first power of theta, and then the derivative of cosine, which is negative sine. And then we can distribute that negative or multiply so that we get negative 2 sine theta. And then negative times negative is positive, plus 4 cosine theta sine theta. And that equals 0. Now, again, we can at least maybe divide out the negative 2. So 0 is equal to sine of theta minus 2 cosine theta sine theta. And let's go ahead and factor out that sine and then solve this trig equation. So you get 1 minus 2 cosine of theta. And let's figure out, well, sine of theta is 0. So when is sine of theta equal to 0? And then let's also figure out when 1 minus 2 cosine of theta is 0, since it's the zero product property. Well, sine of theta is 0. Again, looking at a unit circle, sine of theta is 0 at 0, but also at 180 or a pi. And so even here, we do pick up that extraneous solution because at 0, there's a cusp. But pi is okay because, again, think about what your function looks like for your cardioid. So your cardioid starts at the cusp and goes out in that counterclockwise direction. So clearly 0 would be an extraneous solution. But, again, thinking about how this gets graphed as you move out along this, right, as your radiuses go longer and long, like this, right, eventually you will get to pi. And right at pi, it's perfect for a vertical tangent line, undefined slope. So pi would definitely work. And if you put pi into your function, cosine of pi is negative 1. Where's my function at? Here it is. So cosine of pi is negative 1. So 2 minus a negative 2 becomes 2 plus 2, a radius of 4. So one of the components that has a vertical tangent is r equals 4. The radius is pi. The angle is pi. Now, let's solve the second one over here. So 1 minus 2 cosine of theta equals 0. So this is equivalent to saying when is cosine of theta, there it is, equal to 1/2. And cosine of theta equals 1/2 in quadrants 1 and 4. So a 1 to 2 ratio, 1 to 2, would be a 60-degree angle in the first quadrant or a 60-degree reference angle in the fourth quadrant. So either theta is pi thirds or theta is 5 pi. over 3. And then when you substitute that into your original function, remember our original function is r equals 2 minus 2 cosine of theta. Since the cosine of theta, when it's pi thirds, is in fact 1/2, so we get 2 minus 2 times 1/2, 2 minus half of 2, so 2 minus 1, which is 1. And the same thing you get for 5 pi over 3. So our points would be 1 comma pi thirds and 1 comma 5 pi over 3. And, again, thinking about our cardioid and how it's graphed. So, we go out this way, right? And we're drawing this cardioid. There's kind of a delay in my pen. Here we go. Sorry about that. And so I saw that, right? Like right when, so as we're moving out here, right about at a 60-degree angle, so right there, like if I extended it out like that 60-degree angle, I could put a point, and there's my tangent line, and it would drop it. Oops. It would drop to that, to where there'd be a vertical tangent line, right there. And then, again, keep coming around, and then at 300 degrees, I'd have another one right there. So there are 3 points where there's a vertical tangent line. There are only 2 points where there was a horizontal tangent line. There was 1 point that was extraneous, and then there are 0 examples left because that was a long one. So, I'm hoping that as you start to practice this, you kind of some of the polar functions come back to you. And like I said, I'm not going to test you on graphing them by hand, but you should know about certain features. Like if I showed you that cardioid, you should realize, oh, there's a cusp there. And so in thinking about, oh, well, here's a graph of it, I know it goes in a counterclockwise direction to kind of confirm those things that we can see within the derivatives. Okay, so try the homework, see how that goes, and check Canvas if you have any questions.